Hello everyone, we're going to start on chapter 6 with this video, and in chapter 6 we're going to return back to doing statistics. In chapters 4 and 5 we were doing probability, but now we're going to be going back to strictly statistics, and we're going to be with that for the rest of the class. Also, for the rest of the class we're going to be talking about the normal distribution. We're going to mostly focus on that. And what we mean by a normal distribution is data that if you were to draw a curve or like a histogram or a frequency polygon of the data, that it would come out in a bell-shaped curve or somewhat of a bell-shaped curve. Now, if it's a perfect normal distribution, it would be a perfect bell-shaped curve, but very little data truly comes out perfectly like that. But that would be what we would call theoretical normal distribution, if it was perfectly bell-shaped, perfectly symmetric. We'll talk more about that in a minute. So the topics that we're going to discuss in chapter 6 are the normal distributions, the applications of the normal distribution. So these two sections are very similar. This one just kind of introduces the concept, and 6.2 then shows you how to use it within an application, but it's the same type of computations. And then in 6.3 we're going to talk about the central limit theorem. And the central limit theorem goes a little bit beyond just the normal distribution. There's one little kind of added thing in there. I won't get into it. And then in 6.4 we're going to talk about the binomial distribution. So those are the main topics in chapter 6. And for this video we're just going to do the normal distribution. So we're going to start off with talking about the fact that many continuous variables have distributions that are bell-shaped. And if they're bell-shaped, then we call them approximately normally distributed variables. So the theoretical curve, called the bell curve or the Gaussian distribution, this used to be called the Gaussian distribution after the mathematician whose last name is Gauss, G-A-U-S, and G-A-U-S-S, and can be used to study many variables that are not normally distributed but are approximately normal. So if we think about things in the real world that would be approximately normal, if you think about, say sunflowers, because they can grow kind of tall. So say you're looking at just wild sunflowers and you're trying to figure out the height of the average sunflower, and what would be the likelihood that it would be a certain height given the average of what sunflowers are. So in the middle we would put what the average height is. I have no idea what the average height of a sunflower is. Let me guess and say it's 36 inches. Okay, and of course it depends on what kind of sunflower. But then say it has a standard deviation of 2. Then that would mean that one standard deviation would be 38 inches, 2 standard deviations would be 40 inches, and 3 standard deviations would be 42 inches. And the 3 standard deviations is very important when we're talking about things that are normally distributed, because almost all the data will fall within 3 standard deviations. And we'll get the exact values here in a minute, but this is what they mean by a standard deviation. So if it says that a sunflower is 3 standard deviations above the average height of a sunflower, that would mean in this case, if the average was 36 inches and the standard deviation was 2 inches, that would mean that a sunflower that was 3 standard deviations above average would be 42 inches tall. That's what we mean by these standard deviations. Now, a theoretical standard deviation, there would be no gaps, and this could literally go on forever. Now, we know in the real world that a sunflower can't be infinitely tall, and it can't go below 0 at least. And so in actual world this doesn't go on forever. But in theoretical world, in the mathematical world, we realize that this would keep going on and never actually touch. The x-axis is down here. It would never actually touch this x-axis. It would just get very, very close. And the reason that this is curved the way it is because when we look at a lot of things in the real world, sunflowers, for example, when we say the average is 36 and it's approximately normal, what we're saying is most of the sunflowers would be around 36 inches tall, or at least within a couple inches, or within, at the very least, within 4 inches. 4 inches taller than average, 4 inches below average. Once we get past that, this starts to be pretty uncommon to be 6 inches above normal or 6 inches below normal. So this bell in the middle, this peak in the middle, is saying most of our data is up here. Most of our sunflowers are going to fall in that area, somewhere between 32 and 40. And then as we get down here into the tails of the normal distribution, these things are less likely to happen. And that happens with a lot of things where you have, a typical average, and it's fairly likely to be a little bit off of that, but if you get further off of that, it's more unlikely. So when we're talking about nature or the real world or real data, this comes into play a lot. So this right here is what we call the mathematical equation for the normal distribution. The nice thing is, even though we're going to show it, we aren't going to calculate this. We aren't going to do this at all. So this is the mathematical equation for the normal distribution. This is how you would get a y value, in other words, how tall it is. You'd take e to the negative x minus mu squared over, I can't even see what that is, over 2 times the standard deviation squared, and divide that by the standard deviation times the square root of 2 pi. But we don't have to do that, and so that's the last that you'll see of that. So let's go over and look at some things about the normal distribution. So the shape and position of the normal distribution depends on 2 parameters, and I just showed that in that other picture. It depends, the shape and such depends on what the mean is and what the standard deviation is. So the mean gives you where the middle is, and the standard deviation tells you how much you go up by each standard deviation that you add. So in this case, 36 was in the middle, and then we went up by 2 each time. Well, those numbers can change and be pretty much anything. And so the shape and position depends on where the mean is, because that gives us the middle, and what the standard deviation is, because that tells us how far to go for each standard deviation. And that means that each normally distributed variable has its own normal distribution curve. So if you have a set of data, each set of data is going to have its own mean and its own standard deviation. So let me zoom in on this a little bit. So on this, they're showing us, in these 2 examples, they're showing us 4 different normal curves. So we have the brown normal curve here and the blue normal curve here. And then we have the blue normal curve here and the brown normal curve here. And actually the 2 blue ones between these 2 are the same, because they both have, in both cases, the curve for the blue one is a mean of 0 with a standard deviation of 2. In this one, the brown curve has one thing in common with the blue curve. What that is, if you look at this, what's in common? Well, they're centered at the same place. So they both are centered at 0. So this one still has a mean of 0. So why is this one taller and kind of, gets close to x quicker? Why does it kind of end quicker? And the reason is because this has a standard deviation of only 1. So the standard deviations are at 1, 2, and 3, whereas for the blue one they're at 2, 4, and 6. And so that makes the blue one flatter. It takes you longer to get to 3 standard deviations because you have to go out 2, 4, 6, whereas the brown one you only have to go 1, 2, 3. So these share the same mean, but they have different standard deviations. These 2, we have this blue curve again with a mean of 0 and a standard deviation of 2. And this curve, if we could slide those on top of each other, you could probably tell they're the same shape. But this brown one is shifted over. Well, why is it shifted over? Well, that's because its mean is 2. So its middle is at a different location than the middle of this one. So, this would be 1 would be here. So this is like 0, 1, and 2. Well, for this curve, its mean is at 2, and this curve, its mean is at 0. But their standard deviations are the same, and so how tall they are and how wide they are is the same because they have the same standard deviation. So the mean being different shifts it left and right, and the standard deviation being different changes the shape, the height, and the width. So these are just some properties of a normal distribution. And I'll try to kind of point out when we're talking about theoretical and when we're talking about in actual practice. So these are all, the normal distribution is bell-shaped. The curve is bell-shaped. That would be for whether it was theoretical or an actual real-life situation. If it was theoretical, it would be perfectly bell-shaped, and if it was from actual data, it would be somewhat bell-shaped. It may be a little bit off, but it should still have that general shape. If we are talking about theoretical distribution, then the mean, the median, and the mode have to all be equal, and they all have to be in the center. So we only marked the mean before, but the mean, the median, and the mode would all be the same if this was a perfectly shaped bell curve. Mean, median, and mode would be the same because the average would be right in the middle because it's all nice and symmetric. The median would be in the middle because it's nice and symmetric. And the most often occurring thing would be in the middle because that's where the peak of the curve is. And so the mean, median, mode would all be exactly the same. The normal distribution curve is unimodal, uni meaning one, so it has one mode, meaning it peaks in the middle. And that, again, is if it was theoretical. So and theoretical just means, you know, the perfect mathematical version of it. And then the curve is symmetrical about the mean, which is the same as saying that its shape is the same on both sides. So I'm not going to asterisk this as theoretical because even if it's somewhat normally distributed, you should still have it be fairly symmetric. If it was theoretically a normal distribution curve, it would be perfectly symmetric, and if it was approximately normal, it would be fairly symmetric. When you graph it, it should look pretty good. Then these next two slides we're just continuing with what we were doing here. So the curve is continuous, i.e. there's no gaps or holes. That's only theoretical. If this was real-life data, of course, there's going to be gaps between data. Just because the data goes all the way from, you know, say 0 to 20 doesn't mean you're going to have every value between 0 and 20. So this is definitely a theoretical thing where it's continuous. And again, this is theoretical that it never touches the x-axis. So theoretically, no matter how far you go, it will never get, nothing is impossible. Those tails, you know, should still be a little bit above 0 because any height of the sunflower is possible. But we know in practice that that's not exactly true. So this never touching the x-axis, that's only in theory. And then the last slide on this is that the normal distribution properties for a normal distribution curve, we talked about this back in, I think it was chapter 3. This was called the empirical rule. We talked about it very briefly, and then we didn't really talk about it much after that. But now we're going to definitely be back to it and talk about it a lot. So the total area under the curve is 100%. And within one standard deviation, you have 68% of the data. Within 2, you have 95. And within 3, you have 99.7. So let me show you what that looks like. Whoops, a little bit too far. So if we go to, if we make our curve, let's actually go back to our one with the sunflowers. So if we were looking at the one with the sunflowers, get a different color here. If sunflowers were normally distributed with a mean of 36 and a standard deviation of 2, then the empirical rule says that within one standard deviation up and down, so down 2 inches, up 2 inches, you should see 68% of the data. And then the empirical rule says within 2 standard deviations, you should see 95% of the data. And then I'll have to pop up here because we ran kind of on top of the mean and standard deviation. But if you went to 3 standard deviations, you would see 99.7% of the data. So that means that within 2 standard deviations, you should have almost all the data fall within 32 inches to 40 inches. Almost all the sunflowers should fall between 32 inches and 40 inches. A very few will be between 30 and 32 or between 40 and 42. And then very, very few will be beyond that. So if we go up into this tail up here, this right here, this under this curve is the percentage or the possibility or the probability or the area, however you want to say it. They'll say it different ways at different parts. But the probability of being up here, these two ends together, if between here and here is 99.7, then that only leaves 0.3% left over on the ends. And it's split in half. So this side, you only have 0.15% of the data. And on this side, you have the other 0.15% of the data. Half of 0.3 is 0.15. That's very, very small. So if you were talking about real-life data, 0.15% means 0.15 out of 100. We'll shift that so that we don't have a decimal, and that would be equivalent to 15 out of, shift this decimal over 2 spots in this one, that'd be 15 out of every 10,000 sunflowers. Only 15 out of every 10,000 sunflowers would be up in this area beyond 42 inches. And then the same thing for this end. So only 15 out of 10,000 sunflowers would be less than 30 inches. So this being beyond 3 standard deviations is very, very unlikely with normally distributed data. So you really need to remember that for your homework, for your exam, whatever, that plus or minus 1% is 68, or I'm sorry, plus or minus 1 standard deviation is 68%. Plus or minus 2 standard deviations is 95%, and plus or minus 3 standard deviations is 99.7%. In fact, it's called the empirical rule, but it's also a lot of times referred to as the 68, 95, 99.7 rule. They'll literally just call it by the percentages. So you need to remember this, and that would definitely be a valid question on the exam. For you to remember that 1, 2, and 3 is 68, 95, 99.7. Okay, so let me pause and get the slides set up for the actual problems. Okay, so here is the publisher's nice little version of what we just drew. It has the mean marked in the middle. They didn't give any actual values because this could be really any value. And then they did plus 1, plus 2, plus 3, minus 1, minus 2, minus 3, and then the percentages. These numbers up here, they actually went a little bit more accurate. So instead of saying 68%, they took it out a couple more decimals. So they're saying from the middle to here would be 34.13, and then the middle to here would be 34.13. So together, that's actually 68.26%. So they went a little bit more accurate with these numbers. I think that's a little confusing. I'm not sure why they did that. But just so you understand where they got that from. There's a few questions in your homework that ask you some things like this, so you could refer back to this slide. Okay, so since each normally distributed variable has its own mean and its own standard deviation, then the shape and location of the curves will vary. So for every single set of data, even if it's normally distributed, the mean and the standard deviation can be different. So that makes it a little bit hard to analyze. So what we do when we have data that's normally distributed is we do what's called standardizing the data. And you have probably heard this more than you even realize. When you take any kind of a national test or a statewide test, and they give you, and they when they try to make the difficulty level and things like that, they try to standardize those tests. They try to make it so that most students, when they take that test, will score somewhere around a certain grade. And then the vast majority will score within a certain level. The next group of students will score within 2 standard deviations, and then a very few students will score in the extremely low or the extremely high range. And so those tests are standardized. And what this score isn't necessarily so important, but the idea that we call that 0. So the students that score average would be considered 0. It doesn't mean they got a 0. It means that there's 0 points off of average. So if the average, is 72 and they got a 72, we would consider that 0 because they're not above average or below average. If they score 1 standard deviation above the mean, then we just call that 1. If they score 2 standard deviations above the mean, we call that 2. And if they score 3 standard deviations above the mean, we call that 3. So instead of actually labeling what these are, like with the sunflowers, what was our average? 36. Instead of saying 36, 38, 40, 42, we say 0, 1, 2, 3. And what's nice about that is if we do this to any set of data that we're looking at, then everything has a mean of 0 with a standard deviation, with the standard deviation 1, 2, 3. So you can use tables and charts and calculations the same for different sets of data if we standardize it. Okay, so we standardize the data. And when we standardize, that means we let the mean be 0 and we consider the standard deviation to be 1. No matter what it originally was, we kind of shift it and we say, okay, well, if, for the sunflowers, the mean, the average height is 36 inches, but we're going to call that 0. And the actual standard deviation is 2 inches, but we're going to call it 1 for calculation purposes. And that's called standardizing it. And in order to do this standardization, we need to be able to find out what the standard value is for any value that you're looking at. So all that is finding the z value. We did this actually for just briefly in chapter 3. So in this case, you would take whatever your actual score was. So say we were looking at a sunflower. Let's write this down again. So our average, remember, for the sunflowers was 36 inches. Standard deviation was 2 inches. And somebody said, what's the z-score, or the standard value score, the standard value of a sunflower that is let's have it be above average. So say of a sunflower that is 39 inches tall. Well, the 39 inches is your x. That's the value that you're actually looking at. So in order to find the z value, we would say z equals 39, because that's our value that we're looking at. Then we subtract the mean, so the mean was 36, and then we divide it by the standard deviation. So we're saying this sunflower is 3 inches above average when a standard deviation is 2 inches, and so it is 1.5, 1.5 standard deviations above average. Remember 38, let's fill in this, so this would be 36, 38, 40, 42 with the actual data. And so we're saying that a sunflower that is 39 inches tall is at 1.5 standard deviations, because it's more than 38 inches but not 40 inches. It's right in between them. So this would be 1.5 standard deviations. That's what that z-score gives us. It tells us how many standard deviations above average you are. So what we're going to be doing is we're going to be looking at what's the likelihood of that happening. So what's the likelihood that a sunflower is 39 inches or more? What's the likelihood that a sunflower is 39 inches or less? In order to do that, we're going to have to use a chart. So the chart that we're going to use is the formula table, is on the formula table. And remember that that formula table, it's called important. It's from the publisher, and you can use this on your test. It's called important formulas and tables. And you can either find it in Connect Math under, I think it's Reference. You click Reference, the Reference tab, and then Resources. Or it might be the other way around. It might be Resources Reference. I think it's Resources Reference. And then in D2L, it actually has its own module. So there's a module that literally says, you know, if you go to the Contents tab, one of the modules, you have your syllabus module, your Connect Math module, your exam module. One of the modules actually says important formulas and tables, PDF or something like that. So you can get that at either one of those locations. And or if you bought a book, it should have come with the book. So if you bought a hard copy book, you should have like a laminated version of it. And that is where we're going to have the tables that we're going to use. All right, so let's go over here and see some actual, well, we're getting close to an actual example. So first, it's going to tell us here that if we want to know the area under the curve, which is the same as the probability. So sometimes they'll say what's the area to the left of, or what's the probability that you're to the left of. So they really mean the same thing, because remember that the area, all the area under the curve is 1. So if you say that the area from here down is 0.79, then that's 79% of the data. So area, probability kind of used interchangeably. So to the left of any z-value, if we want to the left, then we're going to just use what's on the chart. And that's because what's on the chart, what they list on the chart, is from a certain z-value downward. So you notice this one, the yellow shading is to the left from both of those z-values. It doesn't matter if the z-value is a negative or a positive, it's the fact that it goes to the left. That's what the chart gives. So we just use the chart value if we want to the left. Now, when we're talking about actual problems, when we get into 6.2, they won't always say left, but what they'll say is below, under, less than, no more than, any of those keywords that kind of give you that idea. It's there downward. Those all are, you know, to the left. So it could say, what's the likelihood that it's 39 inches or less? What's the likelihood that it's below, you know, below 39 inches or no more than 39 inches? What's the likelihood that it's 39 inches or less than 39 inches? There's going to be different wording, you know, for the language versions, but anything that means going downward, this is what we do. We just use the chart value. If they want something above, since the chart gives us below, what it does is you have to take 1 minus whatever you get on the chart. And that's because, remember, the chart gives below. So the chart is going to give you this red part. So if the chart says this red part is 0.2, well, we want this gold part because we want from a certain value upward, so that would mean this was 0.8. So we take 1 minus whatever is to the left will be what's to the right, because altogether it's supposed to be 1. So if you hear above, more than, no less than, higher than, over, any of those words that are indicating that they want that value and upwards, that value to the right, you're going to take 1 minus the chart value. And that would be even if it was up here. So say this was, you know, they were wanting this gold value, and you looked up on the chart and it said this was 0.75. Then what you want is this part, which is 0.25. So 1 minus 0.75 is 0.25. So whatever they're asking you for, if it's to the right, you take whatever's on the chart and subtract it. We'll talk about how to use the chart here in just a second. We're getting there. And then last but not least, if you have a area that's between two values, you don't want to know above or below, you want to know between. Well, what we do is we look up both z-values and subtract. So you'll have a chart value for one z. So you'll have a chart value for z2, let's say, and then you'll have a chart value for z1, and you're going to subtract those. So you're going to look up two different z-values, write them down and subtract them, and that'll be the area in between. Why does that work? Well, let's see if I can get cool with the colors here. So let's say that the first chart value is this one right here. So we'll call this one, oops, that's not showing up very good at all. So call this chart value 2. Call that our Z sub 2. The chart's going to tell you that from there downward is a certain value. So again, let's use some nice numbers. Let's say Z2, the chart value says, is 0.7. Cannot see that. Okay. So the chart says that from that Z value all the way down is 0.7. And then it tells you that this other Z value, let's do a different color here. Say this Z value right there, we'll call that Z1. The chart would say, well, from Z1 downward is 0.3. Well, if I want to know what this yellow value is, that's what was shaded originally, remember, we're going to take the entire yellow value and subtract the red value, and that'll give us the part that's just yellow now. So this is red on top of yellow, but we want just the yellow. And so we're going to take from here down is 0.7, but subtract out this part we don't want. And so the area in that strictly yellow part would be 0.7 minus 0.3, and so in between here, from here to here, would have to be 0.4, the difference between these. And again, we're going to do an example of that, so you'll have a couple times to see it. So now let's see a few actual live examples of this and see the chart that we're going to use. And the first question that we have, it says, find the area to the left of Z equals 2.09. So here's our Z value, 2.09. And in order to find to the left of that, remember, I'll jot this down up here again. If it's to the left, we're just going to use what's on the chart. If it's to the right, we're going to do 1 minus the chart. And if it says between, we're going to use the two different chart values and subtract them. Okay, so we'll look up one value, look up another value, and subtract them. So where do we find that value? Well, if you look on the chart, this is what it looks like. And remember, it's 2.09 is what we're looking for. So on your important formulas and tables, go past all these formulas, and we're going to go to this chart that is called the standard normal distribution. You'll notice it's got a Z here. It's called the standard normal distribution. Oftentimes, I mean, this is the formal name, standard normal distribution chart, but we often call it the Z chart. In this book, it's table E, but Z chart is a pretty common term for it. So we're looking for 2.08. So how do we find that? Well, these Z-scores right here are all negative Z-scores. So this isn't the page we want to be on. We want to go to the next page where it has the positive Z values. And you'll notice it's even kind of nice because it gives a little picture down here to remind you that the area to the left is what the chart is giving. So it's telling you this chart is giving you from that Z value down. So now how do we find that value that we want? Remember the value was, I think I just said 2.08, but I think it's 2.09. Let me double check really quick. Yes, 2.09 is what we're looking for. So we're going to look on the column on the far left. That's our, it says here, this is Z, and it's referring to this row and this column actually. So we look at Z, we find 2.0. So this first column gives us the whole number and the tenths place. So 2.0, and then we're going to go over until we get to 8. So 2.08 is what we want. So 2.0, I'm sorry, I keep saying 8 and it's 9. 2.09 is what we're looking for. So 2.09. So we're going to go all the way over to here, and we're going to go 2.09 and just bring that down until the two meet. So 2.09 would be all the way over here, and that's the percentage of the table, or the area of the table that's to the right of 2.09. So what they're saying is this area right here is 9817, so 98.17% of all the area under here, if this z-value was 2.08. So that's what the chart just told us, that this area right here, this blue shaded part, that's 98.17% of the area, or 0.9817 for an area, because the area is the whole area under is 1, and that's what we're looking for. So 98.9817 is going to be our answer. So our answer is 0.9817. And you can say 98.17%, but in Connect Math it always has you put it as this decimal, so I won't emphasize that. But okay, so let's try another one. Now this next one says find the area from the table, or find the area to the right of z equals negative 1.14. So remember, if we're looking to the right, that's really important. That means we're going to take 1 minus whatever's on the chart. So once we get that chart value, we're not done, because we want to the right of it, and the chart value is going to give us down here. So negative 1.14 is what we're looking for. Let me clear up what we have. Get all this pencil writing off of here so it's not such a mess. I guess I could erase it, that'd probably be faster. Okay, so what we wanted for this one was we wanted negative 1.14. So we're going to look not here on this page, because this page has the positive values and we want a negative z-value. So we're going to go to the other page and we're going to look for negative 1.14. So we're going to go up to this page and we're looking for negative 1.14. So negative 1.1 is here, and then we have to go to 4. Now be careful, because this first row is 0, so it's not 1, 2, 3, 4, it's 0, 1, 2, 3, 4. So it should be this value right here. We'll double check, go up to the top. Yes, that's the column for the 4. Okay, so negative 1.14 gets us 0.1271. So they're saying 0.1271 is this area. But we want this area to the right. So we're going to take, it's not this 12.7%, it's what's left above that. So 1 minus 0.1271, just type that in on your calculator, and you should get 0.8729. And that's the answer that you want. So the probability, or the area above a z-value of negative 1.14 is 87.29%, or 0.8729. But on the chart we get below, so we have to subtract that. And then the final type that you could have is what if you want an area between two values. So our two values here are z equals 1.62 and z equals, is supposed to have a decimal in it, and z equals negative 1.35. So we have to look both of those up. We have to look up 1.62 and negative 1.35. Okay, so I'm going to look up the 1.35 first. I think that's what it was, negative 1.35. Actually, let's look up the 1.62. It's easier usually to look up the big value first, because you're going to subtract, and that's going to have a bigger value. So we'll look up 1.62 and 1.62 we're going to come here to 1.6, and then we're going to come over to 2. And remember, this is 0, 1, 2. So up here above the 2 would be this column, and our number is 9474. So 1.62 gives us 9474. So I'll go write that down. 0.9474. And then we have to get the other value and subtract. So now I need to look up negative 1.35. I'm going to jot it down because I'm notorious for forgetting these numbers. So negative 1.3 is here. And then we're going to go to 5. So this is 0, 1, 2, 3, 4, 5. So if I look up above, I can double check, but that should be 5. Yes, it is. So I'm going to go from the 0.05, come down, and then the 0.13, and they meet at 0.0885. So that's our other number, 0.0885. And then this first number is from here downward. This number is from here downward. So to get the gold part, I take all of this and subtract out the part I don't want. And if I do that, I get 0.8589, or about 85.89%. Something I see students do occasionally is they try to subtract these z values and then just look up one value on the chart. You cannot do that. That does not work. You have to look up the two separate chart values and subtract. So two separate chart values, then do your subtraction. Don't try to subtract ahead of time and find just one thing on the chart. It does not work at all. So here's our answer for that one. And all we're going to do is we're going to do 3 more quick examples and we'll be done with 6-1. So let's go over here. For this one, we're going to use the same chart each time, or the same, the same slide each time, but they gave us 3 different problems. So the first one, it says, find the probability that you're between 0 and 2.53. That's our problem A. So that's a between problem. So we have to look up the z value for 2.53. And we have to look up the chart value for z of 0. So z of 2.53, we go to our chart. 2.53 would be this value right here. So 2.5, and then this is 0, 1, 2, 3, so 9943. And then we're going to go look up the value for 0. Now, we can go look the value up for 0, or we can kind of probably just do it without the chart. We know 0 is the middle, so from here down would be 50%. Now, we can go to the chart and double check that, but it should be 0.5000. So we go to the chart, and I look up 0, and 0 is actually on both sides of the chart. It's negative 0.0 here, 0.5, but or 0.0 here. So 0.5000 is our value for that one. And if I subtract those, then I get 0.4943. So we're saying 49.43% of the data would fall from between 0 and 2.53 standard deviations, or the area between that is 0.4943 if the whole area under the curve is 1. Okay, now I'm not going to go down to these slides because I want you to see it as it goes, and then we'll go down to the slide. So this was A. For B, it says, what's the probability that Z is less than? Remember, less than means we're going to the left. So we can just take what's on the chart. So if it's to the left, we just take what's on the chart. So we just need to find 1.73 on the chart. And that would just be 1.73, just shifted a bit over from this other one that we looked for. So 1.73 would be one more row down and one more column over, 0.9582. And we don't have to do anything more with that because it's to the left, and that's what the chart gives. Okay, so for this last one, it says what's the probability that you're to the right, that you're greater than, so that's right, of 1.98. Well, remember that that means if it's to the right, we have to do 1 minus what's on the chart. So I'm going to look up 1.98 on the chart. 1.98. This would be 1.99, so this would be 1.98. And so we have 9761. And so then our final answer is, I'm going to cheat, what's that when we subtract, 0.0239. So almost 98%. If we subtract that from 1, we get a little over 2%. So there's 3 more examples of an above, a below, and a between. The last thing that they have here is they have one other real quick problem, but this is very similar to the first one that we did. It's a between, and it's just telling you that, remember when you, maybe I was wrong about this, just a second. Oh, this one is actually a backwards problem. So for this one, they're actually giving you the value in between here, the percentage, and they're asking you to find the z. Remember that this z value is 0, though. So what they're saying is we want this little bit right here to be 0.2123. And to get that, I'm going to take some z value and I'm going to subtract the z value of 0, and I'm going to get 0.23. So remember, when it's between, you're going to take chart 1, or I'm sorry, chart 2 is how I've typically said it, minus chart 1, and get a value. Well, we know that 0 on the chart gives us a 0.5. So we're looking for something minus 0.5 that'll give us 0.2123. Well, this has to be 0.7. So 0.7123 minus 0.5 would give us 0.2123. But we don't want this number. What we want is the z that gets us that number. So there won't be any like this on the test, but there's a few on your homework. And so what you have to do with this is you actually have to look in the body of the chart for this 0.7123. So we go to the chart. Remember, we've already got the percentage and we're looking for the z. So we know we want a, I'm going to pause this and clean this up a little. Okay, here we go. So we're looking for 0.7123 in the body of the chart. Well, nothing down here is going to be that big because this is all negative. So from the middle down is going to be all 50% or less. So we're going to go up here. We're going to, again, we're looking for 0.7123. And that's right here. And so our value is, this is the one that we got, 0.7123, so we have to go out and see what z value that is. So if we follow that out, we can see that that's a z of 0.56. So 0.56 would be the value that we would need for this one. So we're saying this z value would be 0.56. So 0 would give us 0.5. 0.56 would have gotten us 7.123. And if we subtracted those, we'd get that. If you're doing one and it doesn't give you, or you don't land on an exact value, because you can see these don't, it doesn't have all the values in here. So let's say you were looking for a value of 9120. And you're looking here, 9120 falls between these two values. So then you just look and you say, well, am I closer to 9115 or am I closer to 9131? And you pick the one that's closest. So for 9120, you'd pick 9115 because it's closer. And so that would be 1.35. Okay, and if it happens, it doesn't happen very often, but it happens to fall exactly in between two, then you pick the bigger z value, but that doesn't happen very often. Usually it's closer to one or the other. So that's all we have for section 6.1. Hopefully that'll get you off on the right foot for doing the rest of chapter 6. And I'm going to mention one thing. I think I talked about that we were doing 6.4, but I don't believe we do 6.4. I think I said at the beginning that we do, but I don't believe we do 6.4. Let me double check really quick. So I'm going to go back on what I said about that. I think 6.4 is one of the sections. Yeah, 6.4 is one of the sections that we skip. So in this, just to kind of clarify, in this chapter we do 6.1, 6.2, and 6.3. We don't do 6.4. So don't panic when you don't see a homework for it. Well, you probably wouldn't panic. You'd probably just be glad. Have a great rest of your day. Good luck on your homework, and take care.